Welcome back friends to the 11th quarter of complex numbers. In this 11th quarter, we are going to deal with conformal mapping. In this quarter, we shall define conformal mapping, we shall define path, we'll deal with some examples, we'll define curves, angle between the curves, then examples, conformality, analytic functions, examples, and more examples. Let us begin our discussion. Intuitively, a conformal mapping is the mapping that preserves angle between the curves. Let us suppose that gamma 1 is this curve and gamma 2 is another curve. They are bearing some angle. We shall define that as theta. By virtue of functional transformation f, we are going to a new picture where we are going to define f of gamma 1 and f of gamma 2. Here f of gamma 1 is along this black path, whereas f of gamma 2 is along this green path. Now the angle between f of gamma 1 and f of gamma 2, we can look from f of gamma 1 to f of gamma 2. So here also we can look from gamma 1 to gamma 2 in this direction. Now to make this discussion more precise, we need to define curves and then angle between the curves. A path in a complex plane from a point A to a point B is a continuous function gamma that rolls over the interval A to B. This interval A to B is over a real variable. So this interval is belonging to real number. That is mapping to a complex number such that gamma of A. So if you perform function gamma on this A, so this will yield to point A. So here gamma of A we are performing. Similarly, we are performing gamma of B, and this B will be mapped to a new point that we are going to call capital B. Now let us deal with a simple example. Gamma of t is equal to 2 plus I plus e to the I times t, where t rolls from 0 to pi. Now e to the it will describe a circle if t rolls from 0 to 2 pi. As t is rolling from 0 to pi, it will describe half circle. We are adding 2 plus I to that, so that is further shifting our circle. Now let us suppose that this one is real axis, this one is imaginary axis, and now we are interested in point 2i. So 1, 2. So this is point 2 on real axis, this is 1i on imaginary axis. So the point of our concern is this one. Now on this point, we are interested in drawing a half circle of radius 1, which rolls like from this point to this point. So this is pertaining to t equal to 0, and this is pertaining to t equal to pi. So obviously here we are talking about interval from A to B, that is from 0 to pi, which is designated here 0 to pi. Now e to the it can be split into real and imaginary part as cos of t plus I times sine of t. and you can couple real part together. So 2 plus cos t will comprise real part, which we can call x of t, and I times 1 plus I times sine of t, that will congruent 1 plus sine t times I, which is imaginary part of our function. Now let's talk about another function gamma of t expressed as 2 plus I plus t times inside bracket minus 3 minus 5i, where t rolls from 0 to 1. Now here we can further simplify this. We can couple together real part, and the real part is 2 minus 3t, and imaginary part is 1 minus 5t. Now we shall try to locate this. The initial point is t equal to 0. So gamma of 0 we shall try to identify. So here t is to be replaced by 0. So here we are left with 2 plus I. So here t is 0. So 5t will be 0. Now let us try to identify the things. Now here we have to go ahead 2 units along real axis and 1 unit along y-axis, that is imaginary axis. So this is our starting point and the end point is 1. So gamma of 1. So here again we have to replace t by 1. So 2 minus 3 will be minus 1 and plus I times we have 1 minus 5, that is minus 4. So in all we have to go minus 1 distance along real axis and minus 4 units. This is 1, 2, 3 and 4. So the next point is over here. So these are the starting points and end points. By our convention, capital A is the functional map of initial point and capital B is functional map of final point. So our function is behaving like this. So smoothly, if you roll t from 0 to 1, you will travel along this linear path, that is a line, in this particular direction. Now we have a very interesting function. Gamma of t is equal to t into e to the it, where t rolls from 0 to 3 pi. Now e to the it is cos of t plus I times sine of t. The whole thing is multiplied by t. So as a real part we can write t cos t and imaginary part is t sine t. Now we shall try and understand how this works. This is going to begin from 0. So gamma of 0 we have to work out. So gamma of 0 you have, that is equal to 0 into e to the power I times 0. Anything raised to 0, 0 into I will be 0. Anything raised to 0 is unity, and that unity multiplied by 0 will be 0. So this is 0. Now you can see here, if you replace this t by 0 and cos of 0 is 1, so whole product is 0, and here t is 0 and sine of 0 is 0. So gamma of 0 is 0. Now the end point is 3 pi. Now gamma of 3 pi we have to work out. By definition, you have to replace t by 3 pi. So here t into e to the it. So 3 pi into e to the power I times 3 pi. Or in another words, if you like, you can write 3 pi into cos of 3 pi. I shall take 3 pi common, so cos of 3 pi. So this is a periodic cosine function and sine function, both are periodic functions with period 2 pi. So 3 pi, I can straightly write pi plus I times sine of pi. Okay, we can now calculate the value for this equation. Now cos of pi, this value is -1, and sine of pi, this value is 0. So in all, the result is -3 pi. So your initial point, which is 0, I'm picking some another color, 0 maps on 0 and 3 pi is mapping on -3 pi. So in between what is happening, we shall try to see. This is a plot I have developed in Maple, and here the initial point is mapping on itself, that is 0. Here I want to mention that this t is a real variable. This is a real variable, and the mapping is going into the complex plane. So this mapping by a function is going into a complex plane. Now 3 pi, when you replace, that is -3 pi. So -3 pi is reaching here. In between what is happening, we shall see. So as the value of t grows, you can work out in between values. If t is equal to pi by 2, what happens? Then if t is equal to pi, what happens? Then t equal to 3 pi by 2, then what happens? I would advise students to work out this, and then this is 2 pi, and then 5 pi by 2. You can smoothly go on developing step by step answer, and then 3 pi. So we are starting with 0. 0 is mapping on 0. So pi by 2, how it behaves? Pi by 2 maps on I pi by 2. So this is the value concerning pi by 2, and this is the value concerning minus pi by 2. So 3.14, 6.28, these are the values you can identify on x-axis, and how it behaves is a wonderful animation. You can see that the function behaves this way. Another example, gamma of t is defined in 3 regions. The first region rolls from t equal to 0 to t equal to 1. In that region, gamma of t is equal to t into bracket 1 plus I. Now let us work it out step by step. This is the real axis. Here I want to mention that the variable t is a real variable. So this r with double bar I am denoting to mention that it is a real variable. Now when t is 0, 0 times 1 plus I will be 0. So it will map onto 0. So here the point that I want to state here is at the origin. So the real number 0 is mapped in the complex plane at origin. As t grows, let us go at the end point. When t is equal to 1, it will be 1 plus I. So here I want to advance unit distance on real axis and unit distance on imaginary axis, such that I am reaching to the point 1 plus I. Now it smoothly sells from this point to this point. In the second part, T is rolling from 1 to 2. So this is 1, next point is 2, and for the third portion, third piece, we are going to reach to the real variable 3. So in this region, real part is T and T is rolling from 1 to 2. Imaginary part is fixed at I. So in the second segment, we are advancing from this point to this point. So this being common, I am again highlighting this. So we are tracking this segment. Earlier we have tracked this segment. Now in the third segment, where T is rolling between 2 and 3, we have gamma of T equal to 2 plus I times 3 minus T. So the initial point T equal to 2, 3 minus 2 will be 1, so 2 plus I. So the real part is 2 and imaginary part is 1I. So here at T equal to 2, this function fixes the same value as here, and when T is equal to 3, 3 minus 3 will be 0, and the real part 2 plus imaginary component 0, so this is flipping to 0. So if you calculate the intermediate values, this curve will go from this place to this, and this way it will advance this way. So here we shall try to define curves. Path gamma over the interval AB mapped onto a complex plane. So here the interval AB is real interval that is mapped on a complex plane C double bar is smooth if the functions, that is real and imaginary, x of t and y of t, in representation gamma of t equal to x of t plus I times y of t are smooth. That is, they have as many derivatives as desired. Now we shall recall the examples 1, 2, 3, 4 just now we have discussed. In the first example, we have considered a function which is semicircle and that was rolling around from point 0 to pi, and the origin was shifted to a new place. The second function that we have discussed was a straight line that was having this type of behavior. The third one that we have discussed was the most interesting one, which started from origin and it spiraled out and it went off to this point. So this is origin and this point was minus 3 pi, and the variation of t was from 0 to 3 pi, and the functional variation was from 0 to minus 3 pi along this spiral line. And the last one that we have discussed was in 3 regions. The first region was like this from 0 to 1. Then in the second region, it went off this way from 1 to 2. And in the third region, it dropped down to real axis this way. So this makes a smooth path it makes a curve, and you can find derivatives as many you want. This is also a nice and smooth. In fact, it is a straight line. The spiral one is also a smooth path that you can call curve, and this one is little tricky. So in the region 1, it is varying from origin to this point. This behavior is smooth. Second behavior is also smooth. The third behavior is again smooth. However, the corners are trouble. So this is not smooth at the corners, and therefore you cannot differentiate this function at these corners. However, the other straight path, curved path, you can differentiate. So this is called as piecewise smooth. So here we are in position to define a curve. The term curve is typically used for smooth or piecewise smooth path. Now let us suppose that gamma is equal to x plus iy in the interval a to b, that is mapped. This interval a to b is again over real variables, and this is mapped into a complex plane C double bar, is a smooth curve, and T0, which is in between A and B. Then gamma dash at T0 is equal to x dash at T0 plus I times y dash at T0. This is a tangent vector to gamma at Z0, which is gamma of T0. Now let us suppose that we have some functional variation like this. Now here we consider a point. This point is corresponding to t equal to T0, and the functional point is gamma of T0. Then we look for a next point in the close neighborhood of the same point, that is gamma of T0 plus h, where h we define infinitesimally small variable, and I would like to mention that this variable h is a real variable. Now the quantity gamma of T0 plus h minus gamma of T0, it will be a vector quantity which is represented here like this, and this gamma of T0 plus h minus, I'll rewrite gamma of T0 plus h minus gamma of T0. This is divided by the number h, which is a real small number. So that doesn't make any change in the direction of this vector, rather it reduces the length. So here we are considering the limiting condition h is equal to, h is tending to 0. This means that we are shifting this point closer and closer to the initial point, and that will make a vector from this to this. So this will make a tangent vector to the curve at the point of definition, that is T0. The point of definition of this is T0. So the tangent vector to gamma at Z0 is gamma dash T0, which is x dash T0 plus I times y dash T0, where dash is representing derivative with respect to the concerned variable. Now we shall define angle between the curves. For this purpose, we shall consider two curves. Let us suppose that this black line, this one, is a curve that is moving this way, and it is going through a point Z0 and it is heading this way in this direction. We have named this curve as gamma 1. Gamma 2 is another curve which is with green color, which is going this way, and it is also going through the point Z0 and it is heading this way, and this is being represented by gamma 2. So here let gamma 1 and gamma 2 are two smooth curves intersecting at a point Z0. The angle between the two curves at Z0 is defined as the angle between two tangent vectors at Z0. So what all we have to do is we have to identify the curve gamma 1 and draw a tangent to the curve at the point Z0. Then we have to identify a tangent to the curve gamma 2 at Z0, and then we have to look at the angle between two tangent vectors starting from gamma 1 to gamma 2 that gives the angle between two curves, and we can define the angle between two curves as theta in this way. Now let us deal with this example. Herein we are going to consider two curves gamma 1 and gamma 2 and trying hands-on to find the angle between these two curves. Let us suppose that for gamma 1 we are considering the range from 0 to pi. It means that in the complex plane we have to identify the argument, and that argument 0 to pi goes this way. For the curve gamma 2 we have pi by 2 to 3 pi by 2. So in this context, the angle of consideration is this one. So that is prevailing in the complex plane, C double bar, and gamma 1 is function of t, where t is a real variable which is belonging to set of real numbers, and that is equal to e to the power it. Gamma 2 is another curve which is 2 plus I plus e to the power it. Now e to the power it represents a circle of radius 1, and theta, when rolls from 0 to 2 pi, it describes a complete circle. But in this case it is limited to 0 to pi, so it is this black line indicating a semicircle above x-axis, and we are heading from the angle t equal to 0 to pi. So this is the terminal point of the curve, and this is the beginning point of the curve. Now gamma 2, the second curve we are talking about, and that second curve is 2 plus I plus 2 into e to the power it. So here you can see that we have a circle of radius 2, and t is rolling from pi by 2 to 3 pi by 2. So pi by 2 to 3 pi by 2 is this much variation with the radius 2, and the center of the circle is 2 plus I. So here you can identify this number on real line as 1, this as -1, and 2 will be somewhere here, and we have to identify 2 plus I. So this is I, 1I is located here. So you can identify the center of the circle as this point. And one has to consider a circle of radius 2 units. That is a curve gamma 2. And we don't have to consider the entire circle. We are considering it from pi by 2 to 3 pi by 2. So this nice curve is passing this way. The point of intersection is real coordinate 0 and imaginary coordinate 1. So the point of intersection here you can identify the real coordinate is 0 and imaginary coordinate is unity. So the ordered pair I can write 0 I, or you can write 0 plus I. It's one and the same thing. Now we have to work out, this is a common point of intersection, and now we are interested in finding the tangent to the curves at the point of intersection. If you want to talk about the coordinates of this point in the polar form, then the radial part is at unit interval and the angular part is pi by 2. So 0, 1 can be represented in the polar form as 1 pi by 2. Now gamma 1 at pi by 2 is equal to gamma 2 at pi equal to I, which is in fact this coordinate. So this coordinate is one and the same thing represented in two notions. Now derivative of gamma 1, that is gamma 1 dash e to the power it will have derivative I times e to the power t. You can split this notation and you can write e to the power it as cos of t plus I times sine of t, and then you can operate differentiation over it. No matter, you will be able to find out the same answer in either form. So gamma 1 dash is I times e to the it, and if you like to find out this gamma 1 dash at pi by 2, why pi by 2? Because we are interested in finding the tangent at the common point. So that will be I times e to the power I times pi by 2. So e to the power I times pi by 2 represents the same point I. So I into I will be I square, that is minus 1. Gamma 2 dash, we have to find derivative of this number. Derivative of 2 will be 0. Derivative of I will also be 0. Then 2 is a constant, it remains as it is, and derivative of this exponential function e to the it is I times e to the it. So 2I e to the it is the derivative, and at the angle pi from this perspective, so here the angle pi is this. So at this angle pi we are trying to find out the tangent, and it is 2I e to the power I times pi. So this quantity is minus 1 obviously, and 2I into minus 1 will be minus 2I. So here one tangent, the first case tangent gamma 1 dash is in this direction, and the second tangent minus 2I, which is heading from this point to I distance. So this is I distance and this is again I. So that makes 2I distance. So they are bearing angle pi by 2. So the angle between two curves is pi by 2. Now here we are in position to define the conformality of a function. Let us go through this definition and try to clear out what conformality means. A function is conformal if it preserves the angle between the curves. Okay, this is a very important point. A function is said to be conformal if it preserves the angle between the curves. More precisely, a smooth complex valued function g is conformal at point z0 whenever gamma 1 and gamma 2 are two curves that intersects at z0 with non-zero tangents, then G operated on gamma 1 and G operated on gamma 2 have non-zero tangents at G of z0 that intersects at same angle. I shall explain you. Let us suppose that we have a curve gamma 1. Let us suppose that this is a curve gamma 1. Then a function is operated, a function g, which we are trying to pose that is a conformal function. So when g is operated on this, it makes the function like this, for example. So this is gamma 1, which is operated by function g. So here g is the function whose conformality test we are trying to make. Now let us suppose that we have another curve, say gamma 2. So gamma 2 is, let us suppose that this curve is, this is gamma 2. Now when g is operated on gamma 2, it results into some another curve. Let us suppose that this curve is g operated on gamma 2. Now these two curves are intersecting at a point z0. z0 is the point of intersection of these two curves. This is a point z0 and this point will be g of z0. Now angle between these two curves we define in terms of tangents. So one has to draw a tangent to this curve at this point. This is tangent to gamma 2 and this one is tangent to gamma 1, and that defines the angle theta, which rolls from gamma 1 to gamma 2. Now we have to identify gamma 1 which g operated on gamma 1 and draw a tangent to that curve at g of z0. So this is the tangent. Then we have to identify g of gamma 2 and draw a tangent to the curve at the point g of z0 and identify the angle theta. Now if theta is preserved, the angle of intersection is the same, then that conformal mapping is, the definition of conformality of the function g, we can say, is obeyed. Conformal mapping in the domain D, let us suppose that this is the domain D, which is for gamma 1 and gamma 2. And imagine a region V on which the mapping is taking place, and in this region V we have G operated on gamma 1 and G operated on gamma 2. Now it is said that the conformal mapping on domain D onto V is continuously differentiable mapping at the, and that is conformal at each point in D and maps on one-to-one on V. So for satisfying the continuous differentiability, this mapping should be conformal, and in addition to that, this mapping should be one-to-one. That is what is expected for the continuous differentiable mapping that is conformal. What all this has to do with the analytic functions, that we shall try to understand. Let us suppose that U is a set that maps to a complex plane C double bar, and this mapping is done by some function, say f, and this function is analytic, and if z belongs to the set U such that f dash at z0 is not equal to 0, then the function is conformal at z0. Thus, we can conclude that the analytic functions are almost conformal functions if their derivatives are non-zero. If the derivative is 0, it is out of question. If derivative is non-zero, then it is conformal. Now let us focus on the reason why this is happening. If gamma is a function which is prevailing in the boundary region between A and B in the domain U, is a curve in U with gamma of T0 is equal to Z0. So here we are defining the point gamma of T0 as Z0, where T0 belongs to some interval between A and B. You can presume that to be real. Then f operated on gamma, derivative of that. So f onto gamma dash at T0, here the derivative will be derivative of the function into the part gamma, derivative of that. So derivative of f operated on gamma will be f dash operated on gamma plus gamma dash, where this gamma is nothing but z0 at t0. So the point where we are considering the intersection. So this makes simply z0. Therefore, we shall replace this gamma of t0 by z0, and we want this f dash having non-zero value, so belongs to complex set of complex numbers except origin, into gamma dash at t0. This represents tangent. Thus in all, f operated on gamma and derivative of that. So f of gamma dash at t0 is obtained from gamma dash of t0, which is tangent, and multiplied by f dash of z0. So here we are considering that f dash of z0. So multiplication of a complex number by another complex number which is non-zero is actually rotation and stretching. So initially if it is like this, then after operation it becomes with different angle and stretched. Then let us have the same theory for another uh, vector or curve gamma 2. Then this is also rotated in the similar fashion and stretched. So actually we are rotating a pair of vectors in the same fashion so that the angle between them is preserved. That is the crux of it. So here we have stated the same thing. Gamma 1 and gamma 2 are the two curves in set U through point z0 with tangent vectors gamma 1 dash and gamma 2 dash. Then f operated on gamma 1 and derivative of it, that is f dash of gamma 1 and f dash of gamma 2, both are obtained from gamma dash 1 and gamma dash 2 respectively via multiplication by f dash z0, which is not 0, which is not 0, the angle between them is thus preserved. I have explained you this. Now here we shall go through one example to realize what theorem we have stated. In fact, we have not uh, given the proof of the theorem, but we have tried to understand the logic behind it. And f of z is equal to z square. That is the example we are considering now. And f dash of z is not 0. In fact, it is twice z. And this is twice z, which is non-zero always. Maps u to a complex plane C, which is restricted to have positive real part. It means that it is restricted to have positive real part. So right hand side of y-axis we are considering. Now this is functionally mapped onto a complex plane C except negative axis. Now this function will be essentially a conformal function because f dash is non-zero always. Let us quickly go through another example. F of z is equal to e to the power z is a conformal at each point in the complex plane C, and we already know that f is analytic function in the complex plane, and we also know that its derivative is non-zero. Derivative of e to the z will be e to the z in the complex plane. Since f is not 1 to 1, why it is not 1 to 1? Because it is periodic. We have seen in one of the earlier lecture that it is periodic over 2 pi I. So by definition it is not 1 to 1 in the complex plane C. Therefore, it is not a conformal mapping from C to C with non-zero number. However, if you choose D to be such a set of complex numbers Z that the imaginary part is restricted to rely between 0 to 2 pi. So here we are considering this as 0 and 2 pi is somewhere here. This dotted line we are ignoring except that we are considering. Now this between region has 1 to 1 mapping, no problem. And in this region that makes the function conformal, and when you map it onto the domain D, then it is in the region of complex plane except origin and positive real, because this is going to map onto the positive real. Now let us consider a very interesting example. F of z is equal to complex conjugate of z, that is z bar, is a 1 to 1 and onto from complex plane to complex plane. However, the angles are reversed. What happens? We have two curves. This one is gamma 1 and the another one is gamma 2. These two curves are intersecting at a point, and the angle between these two curves can be obtained by drawing tangent to these vectors at that point and measuring the angle from gamma 1 to gamma 2 as indicated by the arrow here. Now when one takes the complex conjugate of the function, so the function is taking complex conjugate of the curve, then it is actually the mirror image of what we have on the left hand side. So this nice smooth black color curve has mirror image like this. So that makes it f of gamma 1. Similarly, gamma 2, which is a nice smooth green color curve, its conjugate is reflection of that, mirror image of that, and that goes below the real axis. And here, if you try to look at the angle from f of gamma 1 to f of gamma 2, here you can see the direction of the angle is reversed. Even though the magnitude of the angle is preserved, direction is not preserved, and therefore the conjugate function is not a conformal mapping anywhere.